Welcome back. Today we will discuss about instrument types. So in the previous lectures, we have discussed about the fundamental methods of measurements, which include direct and indirect comparisons. And then we discussed the elements of a basic measurement system, which included primary sensing element, variable manipulation, variable conversion, and all those things. And now, for example, we have now instruments. How do we classify them, and basically how do we design them? We can have a basic classification. That is what we are actually going to study in this lecture. Now moving ahead, so we have first class where we have active and passive instruments. We have null and deflection type instruments. We have analog and digital instruments, contact and non-contact type instruments, intelligent and dumb type instruments. But note that an instrument could be in any of these categories. For example, we have a pressure measuring instrument like bore and tube gauge, which could fall actually into something like passive instruments, null instruments, or even, let's say, contact type instruments. So this is just a broad categories or the classification how we can basically classify different types of instruments based on certain properties. But obviously we can have some instruments which can even fall in many of these categories rather than just one. So now active and passive instruments. In the active type, we have the energy in the output signal comes from the external power source. So if you look at the petrol tank level indicator, so we have a float based petrol tank level indicator. This is the traditional, or you can say the conventional way we would measure the level of the petrol. So we would have a float, or we could say some lighter body that would float on the petrol, and then accordingly we had a lever, and then we had a pivot. So the moment this goes down, this would change the direction, and then accordingly this would change the deflection needle. But this is an active type of instrument where we have an auxiliary power source, though here we may not really need it, but because we just have deflection which tells us actually the amount of petrol in the tank. But we have this classification called active and passive instruments. So this is here acting as an auxiliary power source. It's a battery and you can say a potentiometer here. So what happens is, because of the increase or decrease in the level of petrol or the level of the fuel inside the tank, this float goes up and down accordingly, and then this changes the pivoting point here, which actually changes the resistance of the rheostat that we have, or you can say any other resistor that is placed in the circuit. So accordingly the voltage, the output voltage actually is measured. So rather than the full voltage, a part of the voltage actually is measured, which is actually equivalent to the level in the petrol tank. So these types of instruments where we have auxiliary power source actually are called as active, where active actually refers to the the external power source that is required. So in this case, the energy that instrument derives is the medium that in the measurement also, but the main energy actually comes from the external power source. So here the primary transducer simply modulates the value of the voltage from this external power source. In this case, this is relatively expensive because we have an external power source, we have an external arrangements that we need for this thing. But what actually is the advantage is the resolution. We have a greater control over the measurement resolution because we can actually easily change this resistor capacity, we can easily change this battery capacity and all those things without actually requiring any big change in this system or in this setup. We'll just contrast this with the passive ones. We can actually appreciate the advantages with the active one. So in the passive one, the passive type, it is an example of a pressure gauge where we want to measure the pressure of the fluid. So for example, there's a fluid or the liquid that is coming from here. We want to measure the static pressure of the liquid. So obviously we have seen an example similar to this. There's a piston and there's a rod and there's a spring. So the moment the pressure increases, this piston moves up. Accordingly, the spring gets compressed. So and then the spring doesn't allow free movement. Rather, there's a compressed spring gets compressed, and accordingly this link that is attached here and pivoted at this point moves, so it deflects. So it can actually tell us the pressure of the liquid in the chamber, and accordingly we can get some displacement of the pointer. In this case, if you compare this with the active instrument, we don't have any external power source here. So the output is generally or the entirely produced by the quantity being measured. So the In the passive instruments, we don't have any external source of energy like electric energy or any other mechanical energy. So we have no other energy inputs rather than the measurement itself actually supplies energy to the transducer. That is the one that actually converts one form of energy to another one. In this case, the resolution actually would depend on the practical limits of the pointer arm and this quality of the spring. All right, and these are generally cheaper because we don't have any external source of energy that we want. This is just a piston and a spring and a pointer that we need to actually put in to make such type of instruments. But the main difference is that this is cheaper and the active ones are expensive. The main difference actually lies in the resolution. Now, if we want to increase the resolution of this type of instrument, for example, we don't worry about a spring, we just increase the length of the pointer. For example, the length of the pointer is increased too much. So obviously for a small displacement at this in the piston, we can have a larger actually scale for this. And the moment we have a smaller pointer, and accordingly we have smaller resolution. So but in case of in this case, there will be actually limitations or the practical limitations on the size of the instrument itself, because if we increase this arbitrary the length of the pointer, it will be difficult actually to manage such instruments in the places where we actually want to measure the physical quantity. But in case of active instruments, we just have to actually change the resistance, or we have to change the power source here to actually get a good resolution. So that's why active instruments could be really preferred where resolutions are very important. But if it is just for us, if the resolution can be compromised, then passive one would be actually preferred because of them being relatively cheaper. So this is just a classification. There is nothing like this pressure gauge is an active instrument or a passive instrument. This is just to classify that we can divide instruments actually into these categories belonging to active and passive instruments. And when we want to design, we can also design instruments whether we want them to be involving some energy from our external source, or we want to avoid such things. So all such things are actually used in just for the classification. Then we have null and deflection type instruments. In the null type, we can see here, and as an example again, this is again to measure the pressure in the fluid. So if the pressure in the fluid is measured where we have a piston, but rather than a spring, we're adding weights. We have something called as datum level. It's some datum level is there, which is actually put up as a scale. And the moment we add weights here, this piston goes down. So as per the pressure in the fluid, this piston may go up actually, and then we need to add more weights. All right, so while adding these weights, this will go back to the moment it reaches to datum. This force or these masses that we have added, and because of their weight, or you can say the force, that will balance actually the pressure of the fluid multiplied by the area of the piston. So that the moment it reaches to datum, we can say this total weight actually is equal to we can say divided by the area of the piston is equal to the pressure of the fluid. So this is a null type of instrument where we have something called as it's also called as dead weight gauge. The weights are put on the top of the piston till the downward force balances the fluid pressure. So weights are added till datum level is reached. These types of instruments are highly accurate. Okay, and then we have another class which is known as deflection type. So this is another example of a null type instrument. This you must have seen, in the grocery shops where you want to measure an unknown mass. You have some standard masses on this side. So the moment it goes to zero level, so you assume that this weight is actually equal to this weight. So unknown mass can be easily measured with these standard masses. So it's another example of a null type instrument. So there is another class, or we can say another way to characterize, or we can say classify this instrument as the deflection type. In the deflection type, again the simple same example of a pressure gauge with a spring and a pointer. So in this case, it's merely the pressure in the fluid is actually mainly provided by the deflection of this pointer. So in this case, the quantity of being measured is displaced in terms of the amount of movement of the pointer. So usage wise, this is more convenient and comparatively, because in the case of null, you have to actually go on adding the weights until there is a datum level is reached. But in this case, nothing of that sort is to be done. Simply the fluid goes into this chamber, this moves, and then the pointer points to the amount of pressure that is in the fluid. So there is nothing to be really put up and then to be waited until this datum is reached. In this case, it simply moves the pointer to the point where it actually refers to the amount of pressure in the fluid. So usage wise, this is more convenient and comparatively to the null type of instruments, and hence it's mostly preferred in the workplaces. But in this case, you must understand careful choice and calibration of spring is sometimes required. So the spring may lose its, sometimes its properties. Spring may actually, have some fatigue and other effects, hysteresis effects. So we may have to actually calibrate the spring back, or we may have to even, have a careful choice while we design this instrument about the spring. But if you just talk about the null one, you don't have any spring, you don't have any other issues, you just have a piston, you just go on adding weights. So calibrating weights is actually easier than calibrating the spring. So hence null type of devices would sometimes be preferred, but because of their inconvenience in usage, deflection types are preferred. But when is null preferred is actually when we have to do calibration duties. So null type is comparatively accurate and is actually used for calibration duties. In industry, in many places, we use such methods actually when we want to do calibration activities. Then we have another classification, which is analog and digital. So by its name, analog would refer to a continuous output, you can say, for a given input. And in digital, we actually refer to a particular set of signals or outputs for a given continuous input. So in the analog type, we have stepless variations with respect to time. That means stepless, we don't have any steps. We have continuous variation of the output with respect to input. So an example could be again a bore and tube gauge where you want to measure pressure of the fluid, pressure of the air. This moves, the pointer moves continuously as per the increase or decrease in the pressure. These instruments usually consist of simple functional elements. We have very simple tube and then we have a pointer. These are relatively less cost in terms of mechanical. If we talk about mechanical instruments which are analog in nature, or even electrical ones, they are cheaper and are easy to maintain and repair. An example could be bore and tube gauge. The output generally could be something like this. If you want to even measure it or you want to show it on a graph, output could be like this. So that means this is, if we call this output and this is input, so we have a continuous signal, or we can say we have, for each input we have some output. All right, so this is also called a stepless variation, or you can say continuous variation, or a continuous signal to a given input. So rather than this, we have something called as digital type, where we have discrete steps. We don't have a continuous signal or a continuous output. We have discrete, specific outputs. An example could be of this when we want to actually measure the rotation or the number of revolutions of a shaft or a cam in this case. So if we mount a cam on a shaft, so we can actually measure the revolutions, number of revolutions of the shaft also. It is by using this type of arrangement, mechanical arrangement, where the cam actually hits this mechanical link, and then there is a pivot, and then actually it causes the engagement and disengagement of the switch, and accordingly there's a counter actually that counts from, let's say, 0, 1, 2, 3, 4, and then it counts to second digit and third digit and the fourth digit. All right. So the issue with this type of instrument is that the moment the cam actually rotates, so it can actually, in one revolution, it can give us count as 1. But if it rotates by only half, so we would still get only 1. So for a 1 revolution, you get output as 1. For a half revolution or 1.5 revolution, you can get the output as 1 only. That means there is discrete steps. It cannot move from 1 to 1.5. It can move from 1 to 2 and 2 to 3 similarly. All right, so this is digital, or you can say digital type of instruments. So, but these instruments are generally immune to noise. In digital systems, we have, or digital instruments or digital circuits, the immunity to noise is quite high. So these are kind of a noiseless, you can say, instruments or noiseless devices, which is highly sometimes preferred. And it can be easily interfaced to computer, because computer is our digital device. So because of instruments are preferred for actually control, instruments are preferred for analysis, instruments are preferred for comparison. So obviously computers are these days actually ubiquitously used, and obviously you would like your instrument to be connected to a computer so that you can even control any other device that you want to control based on these input parameters or the sense parameters. So that easy interface is provided to the computer. In the analog one, we need to do something called as ADC, that is analog to digital conversion. Another example is of 4-bit encoder that we have, let's say, for position sensing, or you can say sensing the rotation of a shaft. So this is better than the one that we have just seen in terms of a cam. But again, here we have 16 positions per revolution. So that means now this one has been divided into 16 positions per revolution. So this is quite better than this one. All right, but what happens is, again, sometimes in the control of robotic, or maybe in other various complicated applications, CNC machines and other things, or whenever we want position sensing or velocity sensing, the resolutions sometimes would be, the higher the resolution, the better the control is actually. So this 16 is obviously better than this one, so this encoder is better than this one, but still it has 16 bits per positions per revolution, which means we can measure up to 1/16 of as a resolution. But if we want a resolution better than this, we need to have something called as 1000. We have CPR, which is counts per revolution. So again, this is about resolution, but the question here is about discussing about the digital one, or the digital type, where we say that during this dark region, the output from the LED to the photosensors is null, that is 0. So at this point, it will give us something like 1001 as the output, 4-bit output at this position. But the moment it moves by some degrees, actually finite degrees, so it will still be 1001 until it reaches to this point here. From here to here, we just have one change. So this is 1001, this is 0001. So there is just one change from here to here. So which is actually 1/16 of the resolution. So obviously it means that for a small change from here to here, we will have no change in the output. So that is actually a disadvantage with digital type. But obviously, if you increase the resolution of these devices, so obviously you can actually improve and make them closer to the analog ones. But the biggest advantage is immune to noise, though they are little expensive. They cannot provide values in between two steps, but they could be little expensive also. Another classification is contact and non-contact type instruments. So you must have seen a mercury in a clinical thermometer. So this is a very common example that we see even in our home. We have such type of thermometers. So we have mercury bulb, or we can say mercury here in this bulb, and this expands and goes according to the temperature. It actually increases or decreases. So what classification actually we want to make here is about contact and non-contact type. So contact type, in this case, this actually comes in contact with the measurement. So that is, if you want to measurement of the temperature of the fluid, so it has to go into the fluid. If you want measurement of the body temperature, we have to put it below the tongue or at different places for measurement of the temperature. So we actually get in contact with the measurement. Obviously that modifies the measurement because it takes some energy from the measurement, but it may not be too much, or it may still be very less. But that is what happens actually. It modifies the measurement. But we have to just discuss here about the type of instrument that it is in contact. It has to come in contact to measure the temperature. So it is kept in the measuring medium itself. The examples are clinical thermometer, Borden pressure gauge, and then we have voltmeter in electric circuit, where we have to put that in the electric circuit to measure the voltage across the two terminals. So this is an example of a Borden tube gauge. So we need to put it in a pipeline to measure the pressure. So it is in contact. So the pressure fluid, some other fluid goes from here and then causes deflection of this pointer. So these are the contact type of instruments. And there could be another classification, which is another type, which is non-contact. For example, proximity type or optical type or IR, infrared based sensors are actually, or instruments are actually used these days. They are sometimes very important. We need to actually have these types of instruments in places where actually we want to really avoid coming in contact actually with the measurement. For example, measurement of the velocity of the shaft, or rotational velocity or the angular velocity of the motor shaft, we use something called as tachometers, which are actually non-contact. We don't get in contact with this. It's just some IR signals actually go on this shaft, and then we can measure actually the rotation speed of the motor shaft. So this is a non-contact type example. Another example is inductive sensors. These are again non-contact type of instruments. We can actually measure the distance between the two, between a ferrous metal and this sensor. So we can actually measure the distance. These are also called as proximity type sensors. Or we have something called as ultrasonic sensors. Ultrasonic sensors. These are also proximity type. They don't come in contact actually with the object for whom we want to actually measure the distance between the object and the sensor. So they measure the desired input even though they are not in close contact with the measuring medium. And another example is an optical pyrometer, where it monitors the temperature of the blast furnace, and hence it's kept to be kept in out of contact with the furnace. Another example, variable reluctance tachometer, which measures the RPM of rotating body. It's again similar to what I have just shown you on the left side. Fine. We have the last classification, which is intelligent and dumb type. This is again just a classification. There is nothing really different about these. These days, in the modern times, or we can say in the current scenario, we have most of the instruments are actually intelligent type, where we actually differentiate between intelligent and dumb by just having a microcontroller or a microprocessor actually being embedded in the instrument. These days, you must have seen most of the instruments are digital in nature. You have a digital output, or you have an intelligent instrument where instrument can actually take some calibrations, or you can say many things can be done by the instrument itself. So you have something called as extra sensors on the instrument, where it measures the environmental inputs and automatically compensates that input, compensates the output, and then they are really more efficient. There is something called a self-diagnosis in these instruments, and you can have remote calibration features because you're connected to a microprocessor or a microcontroller, and you can actually communicate from a distance through some protocols like Wi-Fi or radio signals, and then you can actually calibrate that instrument from a long distance, from a remote distance. So microprocessor is part of this instrument. They are relatively expensive. For example, you can see a thermal imaging gun, or you can see a thermal screening gun, where we want to measure the temperature, or we can do many other things. You can see there is an interface provided on the back of this instrument, where we have a lot of other features. So all these features are possible when we have a microcontroller embedded in this instrument, and we can do a lot of other things with this type of instrument. So these are known as intelligent ones. And dumb type classification is just about these normal instruments that we use, which do not have actually microprocessor or any type of controller embedded in them. So they are also referred to as non-smart instruments, and they have basic measurement features. They are without a microprocessor. They need diagnosis and calibration if the need arises, and though they are relatively cheaper. So example is the board and tube that we have already discussed many times.